Welcome to The Explainer. Today we're going to pull back the curtain on something pretty fundamental. How in the world do AIs like GPT actually read our language?
All right, let's just jump right in. This is the central puzzle for any large language model, right? It feels like magic when you use it, but underneath it all, it's really just an incredibly clever translation process.
So, here's how we're going to tackle this. We'll walk through a 5-step journey. First, what's the core problem we're even trying to solve? Then, how do we break language down? How do we give words actual meaning? What about word order? And finally, we'll see the finished product, the final input that the AI gets to work with. Okay, first up, let's really nail down the main challenge here. Because it sounds simple, but it's actually this huge barrier between how we talk and how computers think. At the end of the day, computers get numbers. That's it. They don't understand words or sarcasm or poetry. So our entire job is to figure out a way to take all the richness and complexity of our language and squish it down into a format of pure numbers, something a machine can finally understand. So how on earth do we even start? Well, the very first step, our first solution, is all about breaking language down into smaller, more manageable pieces. This first step is called tokenization, and you can just think of it like this. We're creating a giant dictionary for the AI. Every single unique word, or even just a piece of a word, heck, even punctuation, it all gets its own special ID number. So a sentence to the AI just becomes a string of these numbers. But, this immediately brings up a big question. Which way is the best way to do this? Because it's not as simple as just splitting up a sentence by its words. There are some serious trade-offs to consider, and the choice you make here has huge consequences down the line for the model. And you can see the problem right here. On one hand, you could just tokenize by whole words. Simple, right? But your dictionary would be massive. And what happens when it sees a word it's never seen before? It just fails. Okay, so what about the other extreme? Just tokenize by single characters. Well, that solves the new word problem, but you completely lose the meaning of the word apple if it's just A-P-P-L-E. We need something in the middle, a sweet spot. And that sweet spot, that best of both worlds approach, is a really clever algorithm called byte pair encoding, or BPE for short. This is what models like GPT actually use. It's not about whole words, and it's not about single characters. It's about subwords. So here's how it works. It's pretty smart. It starts with just individual characters. Then, it looks for the most common pair of characters next to each other in the text and merges them into a single new token. And it just keeps doing that over and over. So maybe ES become ES. Then later, ES and T might become est. It does this thousands of times, so it naturally discovers common parts of words, like ing or li, and makes them their own tokens. What you end up with is a vocabulary that's super powerful, but still a manageable size. To put it in perspective, the famous GPT-2 model, its entire vocabulary was built on just over 50,000 of these subword tokens. That's it. All right, progress. We've successfully turned our text into a list of numbers, these token IDs, but we've just uncovered a much deeper problem that we have to solve next. See, the problem is that these token IDs are totally arbitrary. They're just labels. The number for puppy has absolutely no mathematical relationship to the number for dog. To the computer, they're as different as car and galaxy. The model has no clue that they're related. So how do we fix this? The solution is something called a token embedding. The easiest way to think about it is like a giant, super sophisticated lookup table. This is our next layer in the translation process. Here's the deal. For every single token ID we have, this table doesn't just store the ID. It stores a whole list of numbers for it. We call this list a vector. And these numbers aren't random. They're carefully learned during the AI's training, with one simple goal. Words with similar meanings should have similar lists of numbers. And to give you an idea of the scale we're talking about, for GPT-2, each of its 50,000-ish tokens was mapped to a vector with 768 dimensions. That's a list of 768 numbers. These vectors are what allow the model to understand relationships. They create this kind of meaning space where you can do math with words. The classic example is king minus man plus woman, and the resulting vector is incredibly close to the vector for queen. It's wild. Okay, so this is huge. Our tokens aren't just random numbers anymore, they have meaning. But believe it or not, there's still one more absolutely critical piece of the puzzle missing. The question is, does word order matter? Well, obviously, but right now, all the model has is a collection of these meaning vectors. It's what we call a bag of words. The AI knows what words are in the sentence, but it has zero idea what order they came in. Just look at these two sentences. The cat chased the dog versus the dog chased the cat. They use the exact same words, the exact same token embeddings, but they mean the complete opposite. And as of right now, our AI can't tell the difference between them at all. So we need to add one more layer of information. This is called a positional embedding. It's another vector, another list of numbers. But this vector doesn't care about the word's meaning. It only represents its position in the sentence. There's a unique vector for the first position, another for the second, and so on. And the solution is beautifully simple. We just add the position vector to the token's meaning vector. And that brings us to the grand finale. We're going to combine everything we've just done to create the final, super information-rich input that actually gets fed into the brain of the LLM. So it really all boils down to this incredibly elegant formula. You take the token embedding, which captures the meaning of the word. You add the positional embedding, which captures the order of the word. And the result, that final input vector, tells the model everything it needs to know, both what a word is and where it is in the sentence. And that right there is the final input. This tensor, this block of numbers, it contains everything: what the words are, what they mean, and where they are in the sentence. We started with just plain text, and now we have this rich numerical representation. We've basically taught a machine how to read. So now the big question is, now that the AI can read these numbers, what does it actually do with them to understand context and come up with a response? Well, this prepared input is now ready for the next, truly magical step in the process. It's called the attention mechanism, and that is a story for a future explainer.